Mr. Baracus, of course, and I will be your online teaching assistant as we move through the Math 20-1 program of studies. First, an important announcement. According to the Ministry of Instructional Education and Deliverance, I am obligated to read you this message. In an effort to raise morale and to engage students, it is requested that you communicate to them the daily joke. Here it is. Why did nobody want to talk to Pi? Because she just goes on and on and on. All right. Enough of this frivolity and foolishness. Let's do some math. This is a review of some stuff that you need to know moving forward, and it's also something that I believe my sub taught in March sometime. So I want to present this as a first sort of sample lesson, just to make sure we're on the same page and to have you hear what I would have taught had I been in front of you on that day. This is page 115 of your 20-1 workbook, and it's like the third lesson. I call it this is Unit 3, so Unit 3.3, Unit 3, Lesson 3, and it's radicals. We're ramping up to multiplying radicals. And as an introduction, then, we've just got a couple of easy beginning problems here. This one here may look a little silly and it may look a little confusing, but it's here to remind you that what we're doing is we're taking 4 and we're subtracting from it this whole mess. So it's a reminder that you need to expand the brackets and put the 3 down through everything before you do the subtractions, right? So it's not 4 minus 3. Well, it actually turns out to be 4 minus 3, as you'll see in a second. But the way I want you to think about this is keep the 4 in your pocket there and resolve everything in the brackets. And so expand the 3 times x minus 1, and you're going to get 3x minus 3. Just like that. Whoops, plus 3. Oops, my first mistake, thanks. Now, the next step would be to remove the brackets. When we remove the brackets, you got to look at this negative here, because that's really a -1 propagating through, right? You have to distribute the -1 throughout. So it's going to be 4 minus 3x, and then minus a positive is going to be minus 3. Remember I said it would be 4 minus 3 in the end? Just a coincidence. And so when everything sorts out here, we've got 4 minus 3 is going to be 1 minus 3x. Okay? So just a reminder to always keep in mind all that stuff you've learned in the past. Order of operations, expanding your brackets, passing through that -1 through the brackets, propagating the -1 so that you get the correct thing. A common mistake here would be 7. Students would write 7 minus 3x. All right, moving right along here. This, I suspect you'll be able to do and should be doing in your sleep at this point. I mean, the final answer is what? X squared minus 4x plus 4, okay? And how do we get there? Well, it might be easy to remember that x minus 2 quantity squared is the same as x minus 2 times x minus 2, which is really just what? Right? So x squared minus 2x plus negative times a -4, and that's how we get that. Easy peasy, lemon squeezy. All right? So a bit of a warm-up now. Let's leave this for a second and let us have some salad. Now let's attack this, and I think it might be just instructional, just to see how I would attack this problem here, because it's as simple as it looks. If I've got a radical function, a radical expression multiplied by another radical expression, and as long as the root indexes are the same. In fact, these are both square roots there, right? See that imaginary little 2 there and there? As long as the root indices are the same, then it's as simple as this. You take the number in front of the radicals and you multiply them. and you take the number inside the radicals, and you multiply them. Just like that. And it only works, though, if the indices are the same. And in this case, they are, of course. So what do we get? We get 15. And 6 times 20 is what? 3 times 40, what? 120? There we go. We're not done. We never are done. It's never that simple. Because you look at this radicand 120 and you got to ask yourself, can I simplify that whole radical expression? And in fact, you can, because there is a perfect square hiding in there. And you've got to get used to always asking yourself, are there perfect squares hiding inside the radical sign, under the radical sign? Because if there are, you got to pull them out to fully simplify your final thing. So what's hiding in there? Well, ones, but we don't care about ones because that's a trivial example. 2, 3, 4, 5, 6, right? So 2 squared is 4. Is there a 4 hidden in there? There certainly is, and that in fact is what we're looking for here. So there's a 4 times, what are we looking at? 30 here, right? So 15 times the square root of 4 times 30. Now if I pull the 4 out of the house, I have to take its square root. Nice and easy because it's a perfect square. I'm going to get 15 times 2. The 2 comes from the square root of that, root 30. Okay? And 2 times that is going to be 15. So the answer is going to be 15 root 30, just like that. Just to make sure you're fully done, take a look at that radicand 30 and ask yourself again, are there any other perfect squares other than 1 still hiding in there? So is there a 9 in there? Is there a 16 in there? Is there a 25? And so on, right? So there isn't. That's as simple as you can get. And I said 15 root 30. There is mistake number 2. At least I notice these things, right? Without you putting your hands up, 30, right? I'm going to keep a little running tally here. That's 2 little simple stupid mistakes I've made on 1 page in the first 5 minutes. So the fun thing about math is that often, if there are different ways of getting to the final answer, and there are, then you should come to the same answer, even though you're doing a totally different method. So let me show you a different method that we might attack this by. We're going to keep the 3 root 6 in our pocket. We're just going to keep it there. But we're going to deal with and decompose that is simplify into a more mixed radical, the 5 root 20. So 5 root 20 is the same as 5 root 4 times 5, yeah? Sure, because 4 times 5 is 20, you get back to the original. All right? And then if I bring the 4 out, I'm going to take the square root of that. That's going to become 2. So I'm going to get 3 root 6, still keeping that in our pocket, times 5 times 2. There's the 5, and the 2 comes from taking the square root of 4, root 5. And then, if I multiply all of the, I don't know, they're not really coefficients, they're part of the radical expression. 3 times 5 times 2 is going to be 30. And 6 times 5 is going to be 30 as well. And look, we get the same answer, even though we've done a slightly different procedure on it. It's all good. That's how math works. That is not a cocktail. That is water. No, really. All right, let's deal with this one here. Once again, there's 2 ways to do it, to attack this one. These are almost trivial examples because you can do this before having come into 20-1. Let's figure it out. The first way is, well, the rule is that if you're multiplying radicals, just multiply the radicands as long as the base index is the same. And they are. It's all 2, right? So this is going to be the equivalent of 13 times 13, which, as you know, is the square root of 169. All right? You know what the square root of 169 is. It's 13, right? Let's do it just a little bit with a little bit more labor. I'm going to do this just to show you and just to remind you that the square root of anything squared is simply anything, right? Cool. Well, there's another way to do it, and this one is going to use fractional exponents because I want to remind you that fractional exponents are a thing and how they work. We're back to this original expression here. Root 13 times root 13 is really 13 to the power of a half. I'm going to put it in brackets because it's multiplied by 13 to the power of a half, just like that. And you know how to deal with exponents that are multiplied by each other using the rule of you multiply exponents and you add the exponential terms. So it's going to be 13 to the power of 1/2 plus 1/2, which is, lo and behold, 13 to the power of 1, which, guess what, is also 13. So both of these examples here show you that there are often many different ways to dress this turkey, and you will always come back, if you are correct in the first place, you'll always come back to the same answer. And it's a good way of verifying and double checking your work. All right, so poof, we have a new page. This is the next page, page 116. And as you can imagine, things get a little bit more messy and difficulter. And yes, difficulter is a mathematical term. But if you break it down and think about all the rules that you've learned, it shouldn't give us too much trouble. Okay? So what you have here is one rational expression multiplied by a bracket that has two rational expressions. So think if you have something like a times b plus c, or minus c, whatever, right? You just expand the bracket. You're going to get ab plus ac. And if it's minus, then you're just going to subtract them, right? So what's the first step here? What I like to do is, what I'm going to do is I'm going to expand this. I'm going to do this to this without going any further. So this is going to be equal to, I'm going to multiply -2 to the cube root, -2 times the cube root of 12 by the first term, which is 4 times the cube root of 2. That's this expansion here. Minus, and now it's -2, I'm putting it in brackets again, -2 of times the cube root of 12 times 3 times the cube root of 3, just like that. Okay, so I've just expanded these two terms. This is here, this is here. All right, now just use these new rules that you've learned, which is when you're multiplying exponential terms. Oh, and I noticed if you didn't see that there. Does that make more sense now what I did? Yeah, I'm pointing to it and it's off the screen. Still getting used to this whole system and my hover cam and everything else. All right, so what we do is we multiply these two terms and then we multiply these two terms as long as the base index or the root index is the same. And they are, it's both cubed. Everything's cubed, that's good. So -2 times 4 is -8 times the cube root of 12 times 2, which is 24, just like that. Now, minus a negative, it's going to turn into a positive. 2 times 3 is 6, times the cube root of 3 times 12, which is 36. Boom, just like that. All right. Now, got to look for simplifications. There's a simplification here because there is a cube root hiding in the 24, and it is 8, right? So this is going to be -8. Well, let me do a little bit more work here. 8 times what? 3? Yeah. Right? 3 times 8 is 24, cube root of that, plus I don't see any perfect cubes in a 36. I don't see 4. 4 doesn't go in there. Well, 4 is not a perfect cube. I don't see 8. 8, 8, 16, 32, nope. 9, 27, nope, that doesn't work. There are no perfect cubes in the 36, so it doesn't look like there can be much done with that at all. All right, so let's go back. The next line will be to resolve, to pull the 8 out of the house. Well, the cube root of 8 is 2, so I'm going to get -16, that is 2 times -8, -16 times the cube root of 3, plus, and I think we've agreed that there's nothing we can do with this, or as I think I may have said in my notes, can't nothing be done with this. So I'm going to get 6 cube root 36, and I think because the radicands are different, there's nothing else you can do. You don't add this up. This isn't going to be, well, -16 plus 6. It's not going to be 10, -10 root something. This is it. That's as far as you can go right there. All right. So start off with a pretty scary looking proposition, but not too difficult once you just apply some of the rules that you know and love very well. So moving on, let's take a look at this question right here. Alrighty. So now this is a binomial expansion of two radicals. Well, you know what to do with that, right? You got A minus B times C plus D, right? You do that, you do this, you do this, you do that, right? You know, you don't like to use this word, but it's foiling it. Foiling only works with binomials, right? When you have a first, outer, inner class. So you got two terms times two terms. That's a binomial. So how are we going to do that? Do it in steps, okay? Now here's a little trick there. Notice that these both are the exact same thing, except for one's plus 2, one's minus 2, right? So do you remember your perfect square trinomials? That's what this is, right? So the answer is going to be just two terms. So this times, let's see, this times this is going to be a thing. So let's put that down. So we're going to get 4 of square root 5 times 4 square root 5. In other words, 4 root 5 4 times the square root of 5 quantity squared, isn't it? This is really like this. I'm just, that's just that, right? All right. Okay, so that's this term here. Then we're going to get 2 times 4 root 5 minus 2 times 4 root 5. So the inner and the outer, these middle two terms here are going to cancel out. They're, oh, that's mistake number 3. You can tally. Maybe even 4. I don't know. A cat and a little kitty cat in the Amazon rainforest has died. We canceled out. But then we just got the final thing to do here. Negative 2 times positive 2 is going to be negative 4, right? So remember that anything squared, this resolves both on here. So this is going to be 16. And then the root 5 squared is just going to be, well, anything squared. The square root of anything squared is just going to be itself. Like that. Minus 4. And finally, now we do a little bit of mathemagic here. 5 times 16 is what? The same as 10 times 8, right? So 80 minus 4. And our final answer will be what? 76? Yep. Yippee-ki-yay. We got it. Onwards. We are still on page 116. This is question 2A now. Let's see what we got for 2A. See, we're getting messy and messier here, right? There's a little reminder right here about multiplying difference of squares, right? Which give you that funny sort of, not perfect square trinomial, but you know, that funniest. Water, by the way. No, really, water. So remember that a minus b times a plus b is simply a squared minus b squared, right? Difference of squares. Difference of squares. So you got to use all of these little things that you've learned up until now, right? We started last year in 10C. Now in 20-1, we really solidified the idea of the perfect squares and perfect square trinomials and all that stuff. Okay. And you always got to look for the simple way to do things. Otherwise, you create more work for yourself. And when you do more work, theoretically, you'll get the same answer, but you just expose yourself to the possibility of more error. All right. Well, this is a monomial times a binomial, so we're going to do 2 different multiplications here. And so you just got to keep them straight. And by now you're learning that rule to help simplify this. So I'm going to multiply these first 2 terms. Negative 2 times positive 4 is negative 8. And because it's a square root, they're both square roots in the radicals, then, let's go a little bit like this. Then you simply multiply the insides. So we're going to get 11. 2 times 11 is 22. And c times c cubed is going to be c to the 4th, just like that. Okay. So there's the first 2 terms multiplied by each other. minus now the second two terms multiplied by each other. Once again, well, we've taken care of the negative already, but it's a negative 2 here. Normally it would be negative 2 times positive 3 is negative 6, but it's a minus a negative, subtract the negative, and you get positive again. So there's the positive 6. And because these are both square roots, you simply multiply the radicands by each other. 3 times 11c is going to be, I think, 33, square root of 33c. Good. Easy peasy, right? So just break it down to steps. That's all you need to do. All right. Now, the radicands are not the same, so we just can't add them. So that's the first thing you look for. If the radicands were the same, then you could resolve the addition, right? But they're not. So now all you have to do, or all you can do, is look for simplifying inside. So is there a perfect square of anything hidden inside that first radicand? And I would say, well, not with the number, but certainly with the c, right? So c to the power of fourth, square root of c to the power of fourth is c squared. So we can simplify this a little bit. So we'll take the c to the power of fourth out of the square root, and it becomes c squared, right? And then there's nothing we can do with the root 22, so it'll stay. And I cannot see anything that we can do in here. I don't see any perfect squares hidden in there. 6 root 33c. And I know this looks a little bit ugly and not very satisfying, but that's the best we can do. And sometimes the best you can do is the best you can do. All right? Now, one more complication. Remember when we were talking about square roots of variables? You have to now deal with and state your restrictions. In other words, you can't have a negative radicand. What does that mean? Well, you see the c here? It means that c must be greater than or equal to 0. C cannot equal a negative number because you can't take a square root of a negative number. And so we need to state that restriction. This is a new thing. You're going to have to do this forever now in your mathematical careers. All right. So now you just know things are going to get messier and messier, and in fact, they are. So let's take a look at this mess here with me. Everything is reversed on the camera, right? So we've got 2 times the square root of 3a plus 3 times the square root of 4a quantity squared. You know what? I better do. 2 3a plus 3, oops, that looks like the cube root, don't it? I've convinced myself that it is easier to write out the first expanded form. That's good for me. It means more writing for you. Oops, I drew the bracket in the wrong place here. There we go. Right, that's what this squared means. It means this times this. So we're going to take these two terms here, okay, and now the 2 times 2 is 4, and the root 3a times root 3a is it's the same thing as this, isn't it? And I'm going to write that there because the square root of anything squared is going to be itself. So you know that this first step is going to be 4 times 3a. You know that, right? Okay. What else do we have next then? Well, you've got 2 times 2. We did this. Now let's do this. It's going to be 6 times that mess. But these are the same thing, right? So it's going to be another 6 times this mess, and this mess and this mess are the same. All of this to say is that it's going to be 2 times 6 times, and now multiply the insides. So, or the insides here. So we're going to get square root of 12, and then 8 times a is a squared, just like that. And then finally, the outer terms, this and this, we're going to get simply And again, I'll do it a little bit longer. The square root of 4a quantity squared, right? So this is the first terms multiplied by each other. This is the first and last and the inner and the inner terms. And there's two of them, so that's why it's 2 times 6. And then finally, the last thing, quantity squared. Boom. So let's simplify it. Square root of anything squared is itself, so that's why we get rid of the square root sign in this part of the expression. This is going to become 12 times 12a squared. Nothing we can do with this except multiply out the result of 2 times 6. And then again, the square root of anything squared is simply going to be, itself. And the only thing I forgot to do is, you see this 9 here? 3 and 3? This should have been a 9, which means that this is going to be 9 times 36. That's mistake number 5. Keeping track? I'm not. All right, good. Take a moment and just take a look at the steps. This is simply a binomial expansion that comes from this here, okay? So multiplying the first terms, the outer terms, the inner terms, and the last terms, and that's what this is all here. The only thing I've done is I've combined the two parts of the binomial expansion together to save some time. And again, by this point in your mathematical careers, that should be pretty straightforward for you and easy. All right, let's see if we can simplify this mess at all. We have a's, we have a's. Well, 3 times 4 is 12a. I'm going to bring this a over here. 9 times 4 is 36. Okay, so there's all my a's together. And take a look at this now. I'm going to keep the 12, but you have to ask yourself, are there any perfect squares hidden in 12a? You see the 4? It's 4 a perfect square? It sure is. So if I take the 4 out of here, it's going to become a 2. And you'll be left with 3. Now, let's do one more thing here. Okay? Look at the a squared. Is that a perfect square? Sure is. What's the square root of a squared? A. So I'm going to get the 2a. The 2a comes from 4 times 3, which is part of the 12, and the a squared. Square root of 4a squared is 2a. And when I take 4a squared out of here, I'm going to be left with just 3, just like that. All right, what next? Anything else? Oh yeah, the 3 times. Okay, I've already done this over here, right? So this is here, this is here, and then this resolved is here. All right, next step. 12 plus 36 is what? 48a? What's 12 times 2a? 24a. And I can't do anything with the root 3. There we go. Now that looks really messy, but it's the best you can do. It is the most simplified expression that you can come out of this. Now, there's no variable in the radical sign here, so we don't have to worry about a being greater than 1 or less than 1 or whatever. But, what if a were negative here? Or what if a were negative here? Well, you'd be taking the square root of the a up here. And you can't do that because the square root of a negative number, as far as you know, I mean, you know that there's something called complex numbers or imaginary numbers, but you don't know what to do with them other than that they have a name. So because the a cannot be negative here, you have to state your restriction on a. A must be greater than or equal to 0. Because a cannot be negative up here, because it gives you a square root of a negative number, and that is not allowed. All right, so what's happening in a lot of these questions is that you're not getting really nice solutions. Now that doesn't look pretty at all, and up to this point, you've been used to getting nice, simplified answers. And so you've got to get the message that your answers now are not going to look pretty. Even when you simplify as far as you can, they're not going to look pretty enough. So Always look for simplifications, but try not to oversimplify or think that there's more to do when really there isn't. All right. So here we have a total dog's breakfast of a mess of something. We have two binomials. And again, you've been doing binomial expansions since last year now, right? So the difference is trying to figure out or trying to deal with these radicals inside here, right? Now you already see a radical, or you already see a variable inside of a radical. So right off the bat, you know that C cannot be greater than, or it must be greater than or equal to 0 in this case, right? Because you can't have a negative radicand, and so at the end, just keep in mind that you're going to have to state and declare your restrictions. All right, step by step, what do we do here? There are 4 multiplications. These are not conjugates of each other. They're totally different expressions. Step by step, let's take the first 2 terms here. 2 times 5 is 10. And because they're both the same index root, they're both square roots, then I just multiply the insides. What is C times 3C? Well, 3C squared. There's your first multiplication. Let's do the second one first. What do I do next? 5. All right, so minus 1 times negative 5C, so that can be minus 5 root C. Cool. Then I'll do now the inner ones here, 2 times 2 square roots of 3C plus 2 times 2 is 4 square root of 3C. Cool. And then finally the last terms, 2 times negative 1 is negative 2. Cool. All right. So now you look at trying to collect like terms. You look at trying to simplify the entire radical into a mixed radical, or if it's already a mixed radical, see if you can't make it even more mixed. You know what I mean? Look for perfect squares. All right. Well, I don't see anything you can do here. There are no like terms to collect. Right? C and 3C are not like terms. I don't see any perfect squares. Well, actually, I do see a perfect square there, right? So if I pull the 10C squared out, it's going to become, or the C squared out, it's going to become 10C. So that comes out. And I've got the square root of 3C. No, of 3. Yep. Minus 5C. 5 root C. Yep. Plus 4 square root of 3C. And minus 2. Good? Yep. Look, you're going to want to look, you're going to want to do something. I know some of you just ate and look at that. Root, square root, root C, and root 3C. They're not the same. There's nothing you can do to combine or simplify that. It is what it is. The final answer is 10C square root 3. That's funny, it's square root of 3, square root of C, and just to mess with your minds, square root of 3C. Wouldn't it be nice if you can combine them all? We can. That's all you can do. Okay? Minus 5 root C plus 4 times square root of 3C minus 2. Nothing else to do except state your restriction. C must be greater than or equal to 2. And I made a little note in my class notes. Beware of trying to look for simplifications that simply don't exist, because sometimes they do not. So as you can see, I've had a little bit of a hiccup here. I went off on a tangent and forgot one little step, and so let me retrace my steps and try to explain this again. So the deal with this one is it kind of looks like 2 binomials multiplied by each other, but it's not. What you have really is this 4x times the cube root of 54 minus everything after it. So this term times the first minus this term multiplied by the second. So you got to do those in steps. And so what I'm going to do is I can keep the minus. I'll do a big bracket around here. Okay, because it's minus everything here. So what goes on here? Well, let's multiply these first two terms first by each other. And we're going to get 2. And inside the brackets, or inside the radical sign, because they are both cube roots, the root indices are the same. I'm just going to multiply 3x times 18x squared. And in so doing, I'm going to get 54x cubed. So that's the first two terms multiplied by each other. Now I'm going to go minus, and I'm going to multiply the second two terms by each other. And in so doing, I'm going to get 10 on the outside. And once again, because the root indices are the same, they're both cube roots, I'll multiply the inside. So 3 times 18, or 6 will be 18. And, yep, I'm doing the insides. And then x times x to the third will be x to the fourth. And I've already got a y to the fourth there, and that's not going to change. So that's what I got there. Cool. All right, so let's do a little bit of simplification and do a couple steps. What you're trying to do is combine like terms, and you can't combine like terms until all of your radicals have been fully simplified into mixed radicals. So you're always looking for something to take out of the house, right? Or because this is a cube root, you're looking for perfect cubes hidden in there. And there in fact is. Do you see the 9? 9? No, not 9. 3 times 3 times 3, so 9 times 3, 27. Do you see the 27 hidden in the 54? Sure you do. It's a 3, right? 3 times 3 cubed. So I'm going to pull out a 3 out of the cube root of 54, and on the outside of the bracket, I'm going to have 4 times 3. I still have the x, times the cube root now, and because I pulled out the 3 times 3 times 3, the 27, I only have cube root 2 left in there, just like that. Now, I'm going to start removing the brackets as well. Oh, I should have put a closed bracket there. When I remove the bracket, it's still going to be minus this mess here. And you see the 54 here? You see the 54 here? Same thing, right? There's a 27 hidden in there. So this is going to be minus 2 times 3. And I'm going to have inside the brackets then 2x cubed. Now, something you might be seeing that I can go a little bit further here. I just wanted to break it up into 2 steps. So yes, you can, but let's do it step by step. All right, the last term here. Now, minus, I take the brackets away. Minus is going to become a positive 10. There's not much I can do with the 18x to the 4 to y to the 4, so I'm just going to keep that all in there. 18x to the 4, y to the 4, but it's a cube root of that. All right. And now I can continue on my simplifying step here. 4 times 3 is going to be 12x times the cube root of 2. Okie doke, that's good. Now, remember I said that there was some more to do here. Oh, this should be a 3. Forgot to write that in. All right. What's the cube root of x cubed? X. So I'm going to multiply 2 times 3 to give me my 6. But I'm also now going to pull out an x from the x cubed. That's going to be 6x. And so inside here, I'm simply going to have cube root 2 again. All right. Plus 10. And you got to look now at the x to the 4th and y to the 4th and ask yourself, are there any x squareds hiding in there? And there most certainly are. And I'm going to write this down, so don't write this. But if you recognize that x to the cube root of x to the 4 is the same as the cube root of x to the cube times x squared times x, right? The cube root of any number cubed is simply itself. So this is going to resolve itself, bring it out of the house. It's going to become x. And I'm going to be left with cube root x inside, right? So there is most definitely stuff I can pull out of here. And in fact, I will start by bringing the x out and bringing the y out. And what am I going to be left with? The cube root of 18, because I can't do anything more with that, x Why? No. So I'm going to erase this now. If you want to pause and write that down as a note, maybe down lower, just to remind yourself what I did with the x squareds. I love erasable pens. All right, go away. This is water. No, really. All right, so what do we got here? I got 12x times the cube root of 2 minus 6x times the cube root of 2. Notice that these are like terms. 12x minus 6x of the same stuff is simply going to be 6x times the cube root of 2. So that deals with all of this. And I've just got this left now, plus 10xy times the cube root of 18xy. Boom, just like that. We're not done. You still got to look for restrictions. Now, if you take a look here, because it's a cube root, remember you can take the cube root of a negative number. So x and y do not have to be greater than or equal to 0 here or here. Okay. Anywhere else? No, it's all cube roots. So you're allowed negative numbers in the radicand. So it doesn't look like there are any restrictions on the x and the y. You still have to say that. So you're going to have to say x and y are members of the reals. You have to state that. That's a roundabout way of saying there is no restriction on the x and y, but it's there. All right, this video has gone on long enough. I am going to cut out a little bit here and suggest that this last question is kind of fun, but not absolutely required. The solutions will be posted, so if you want to go take a look and use that as a guide, go for it. But I mean, you start off with this, right? You got a triangle, okay? And one side is 3 root 7, I think, which means the other side is 3 root 7, right? And then the base is root 20. You should be able to figure that out, right? Use half pi or 1/2 base times height to figure out areas and all that. It's all good. All right, take care. Why does nobody like to talk to pi? Because they go on and on and on. Happy mathing. Holy crappity.